In this last part of the unit on compression, I want to talk about some tricks that you can do specifically for natural language text, and it applies to other data too, to help compression, even though the methods that we will discuss in this part are not by themselves compressing the text in any way, but they help subsequent compression stages, as mysterious as that sounds. So to motivate this a little bit, we saw a couple of different compression methods. There are the three main ones again, and here's what they can exploit, what they can use. Run length encoding obviously profits from long runs. Huffman coding profits from characters that are much more frequent than others, and Lempel-Ziff-Welch can exploit repeated substrings, in particular if they're not too far apart. However, those methods can be frustratingly blind to some ways that sometimes a text cries to you that it is compressible, but the compression methods don't seem to find it. For LZW, it could mean that the repetitions are too far apart, so that the dictionary is already flushed. And I might add, this is not an academic concern. People are currently looking at genomic databases where you have genomes of several individuals, say several thousand humans, who have their whole genome sequenced. That's a massive amount of data. And well, of course, the genome of every individual is a little different, but to a large degree, our genomes are very, very similar. There's large parts that essentially are the same, just with small local differences. And it's true, well, a human genome is roughly, what is it? Okay, I forget the numbers. It was roughly 3 to 4 gigabytes encoded in the trivial way. So that's way beyond the usual data dictionary sizes for zip compression. So just as one application, repetition might be present in your data set, but it's too far apart for Lempel-Ziff-Welch methods to reasonably find it. Similarly, for Huffman codes, if in the total text the frequencies can be very balanced, but still locally it could be that some characters are much more frequent than others. And so you would like to exploit this locally skewed character distribution, but Huffman codes, in the way I described it, taking the total frequencies, just are not able to exploit this. And for run length encoding, it's very easy to come up with little examples, like just AB, 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 AB. If you have a run of a pair of character or a longer string, run length encoding doesn't compress this at all, but it seems that it's very, very repetitive. So there's different ways in which an input text can be repetitive, but our methods don't seem to exploit this. And this is where text transformations can help. In principle, we understand text transformations are any functions that take the text, so they take the source text, they map it to some other transformed text, which is not necessarily any smaller. So you can encode and you can decode. So they have to be invertible, which means you can go back and forth. But by themselves, they're not very helpful for compression. The source text and the transformed text, in the extreme case of the BWT that we'll discuss, they're really the same length and they have the same characters, but still it's true that the transformed text has some properties that can be exploited for compression. So whereas this part is true for any compression method or any encoding, text transformations have additionally the property that they're not helpful in isolation. But they can help our compressors to see the existing redundancy. So they're not magically creating redundancies. They have to be invertible, so they can't really make anything appear that wasn't there before, but they can make it exploitable for the particular compression methods we have discussed. There's two of these that I would like to discuss. The first of the text transformations is the move to front transformation. And for that, I should first tell you what move to front is. It comes from an entirely different field inside algorithmics, namely that of self-adjusting data structures. And in the case of move to front, it's a very simple data structure. It's just a linked list. The setup is as follows. You have a list of objects. So these are little boxes. Let's just call those by some names, so letters. And this doesn't have to be sorted. They're just in any order, whatever objects you might have. And this is a linked list, so it can continue. Yeah, where is it? Here. So okay, I have to be a bit more careful. So this can continue. It's a linked list of an arbitrary length, and it stores a set of objects, not necessarily sorted order. Now, when I access an element, say element D, the only thing a linked list can do is I can start at the beginning, and then for every element I can find the next. So I can linearly walk through the list. First this, then I walk to this, then I walk to this. So I have found my element eventually, and then I can do whatever I want to do with this element D. Maybe it's a dictionary that maps D to a certain value. But then after I'm done with element D itself, I rearrange the list. So I change the order of the items in the list. And for move to front, what I do is I take this, make it the beginning of the list. So here's my start pointer, then comes the D. And the rest of the list I just keep unchanged. So this one will connect here. And then I will have A, C, B, E in the same order they occurred before. That's the idea behind move to front. Whenever I access an element, whenever I need a certain element, I make sure that after the access, it's the first one in the list. Why would this make any sense? The cost of accessing an element, if I start at the beginning and scan sequentially through the list, is exactly the position in the list. If I access D, the cost is 3 because I had to traverse through the first 3 elements. If I access D and then access it right after that again, D is at the beginning of the list, and now the cost has shrunk to just 1. That's the idea of move to front. If you access the same thing again or soon again after you've touched it the last time, it will still be in the proximity of the head of the list and will be cheaper to access. In that sense, you could say move to front learns the probabilities of access to objects. The ones that are accessed more often tend to cluster at the beginning of the list, and the infrequently accessed objects lingering around at the end. All right. Before we continue with that, I'd like to jump to this question, just to test your understanding of this and to wake you up a little bit. I'll try to start it on the phone so you can have a look at this and try to figure it out. Okay, there you go. All right, as always, if you want to let me know that you're done, please do so. I'll wait a little more to give everyone a chance to vote on this. Unlike the mean trick question from the beginning, this one doesn't have any nasty surprises. It's just testing that you paid attention. And once we're done with that question, I'll open the Pingo login again. Okay, I finally get some dones. Maybe wait for a few more. All right. Okie doke, so let's do the table view. Again, this capitalizes stuff, not very helpful. Okay, we accessed A, so A should be in the front, and then X, Y, Z doesn't change the relative order. An easy way to solve this task, in case you're ever asked the same question again, is you just delete the thing you access and put it in front of the others, not touch anything else, and then that's your answer. Okay, well done. So we understood how move to front operates, and you might also imagine that it's actually a good idea to use this if you insist on having things in a list like this. It would bring the objects that are accessed often to the front, so making it cheaper to access them, whereas the others that are not needed can take the more expensive back seats. What does that have to do with compression and text transformations? We'll use the same idea. We'll use a move to front list for storing the alphabet of our text. And if we want to encode the next character, we access it in the list, well, in the sense of MTF access. But before we move it around, we encode the character using its position in the list. Okay, so we replace characters by indices. That also means the code words are integers from that range. And after we encoded a character, we then apply the move to front transformation to the list. You can think about why we don't first move it to the front and then encode it, but if you think about it, you will figure it out. This is the right way to do it. And let's first see how this works in a second, but you can already think about what this does to the text. If we have a location in the text where, for whatever reason, there's just a few characters that occur all the time, that would mean those characters stay near the front of the list, and then accessing them, well, it's cheap in the move to front heuristic. Here we don't really care how cheap it is to access them in the list, but we care about the output, and that would be many small numbers. So we have a local property in the input string, clusters of characters. In a certain area of the text, certain characters are more frequent, and that translates into many small numbers. So that's something we can globally exploit, say with Huffman codes. That's a local feature that we could not exploit with Huffman codes. That's how the move to front heuristic, that's one way how the move to front heuristic can help. Now, before we go through an example, here's the code just to show how simple it really is. At least if you don't spell out what the MTF means. I left this as just plain text. The idea is to show how encode and decode, okay, it's so similar that I didn't notice that I copy pasted that. So to encode, you start with a list containing all the alphabet symbols. Then you go through your text character by character, encode each character by its position in the list, and then move it to the front. For decoding, you do the very same thing. You start with a list of all the characters. You decode the first character by looking at the position in the list that you read. Then you decode that, and then you move this character to the front of the list. That way you emulate, again, exactly the decoding has to replay the same changes that the encoder has done. Here's a small example. So we have the word inefficiencies that we want to encode, and here's the Latin alphabet initially in sorted order. So the first step would be we find the position of I. I is here. So the first step is encode this with 8. And then we do the move to front. So I is taken out of this and moved here, and all the others are shifted one position to the right. So I hope you're able to see this, that here A, B, C, D, E, F, G, H, they're still all together, moved one position right, and I is at the beginning. Now the next step is N. So we find N in the list, we encode it using its index, and then we move it to the front, shifting everything that's between N and the front one position to the right. Then we encode E, and I think I'll fast forward through this a little bit. It's the very same thing that happens all the time. So in each step, you find the character in the list, you note down the position where you found it, and then you put this character at the beginning of the list and shift everything else back in line. All right, once you've done this, you encode this with this coded text of numbers, a bunch of positions. Now, at a first glance, it maybe doesn't seem very noteworthy, or it doesn't seem very useful to do this. So if you look at it a little more closely, you might see that if we have a run in S, so characters repeated in S, that's for example here the case, FF. It's a little hard to see, but maybe should connect this a little bit. So this is the characters. So you see, a run always translates into a bunch of zeros. The first character is whatever, but then all the following occurrences of the same character must be a 0, because that character has just been brought to the beginning of the list. So that's something 0, 0, 0, 0 if there's a run of length 5 in the source text. And on the other hand, if we find a run in C, for example, the 3s here, in the coded text, what does that mean? Well, that's a little more interesting. So we find the 3, 3, 3 stands for this phrase CIE. And if you go 3 positions back, 1, 2, 3, you find the same, so that's -3. You find the same substring again. So if there's repeated substrings plus the condition that the characters are unique and none of the characters occurs in between, then you get a run of one character. So this one is a little, there's some repetition going on. It's unfortunately not as simple as saying any repetition in the source text translates into such a run. That's not quite true. But if you have a run like this, then there will be some form of repetition in the source text. So that's just a hint that move to front can be useful. It transforms runs into other runs, so it doesn't destroy runs, and it might transform repetitions into something that's even easier to compress, namely a run of the single a single number. As I said before, move to front itself does not really do much of a compression task. For one thing, because we still have to encode those numbers, and also by itself it's not very effective. But it's a key component in other pipelines, and in particular following the next transformation that we'll look at. If we want to use this, we still have to encode the code words, so the integers. And there you have two options. You can take Elias gamma code, which is a good idea if you expect your text to have these local clusters, because then you will find more smaller numbers than big numbers. And if you can afford the second passes, a Huffman code is always optimal to represent individual characters, so why not use it here? But again, the prime example of where move to front is really shining is in combination with the BWT.